dive into the exercise set for today. And this exercise set is going to encompass not just the modeling and formulating that we just went over, but it's going to also hit on some of the topics from the videos that we had earlier. So if you were unable to watch any of those just yet, something popped up, then maybe make sure you can watch those at your convenience, and then come back to some of these questions if they don't make sense. Let's go over sort of the process that I want to have for this session. There aren't a lot of questions because sort of making sure that we have enough time for everyone to dive in and go from there. So this is going to be a little bit less structured in terms of what we're gonna do. We're essentially going to I'm going to give you guys about maybe 10 to 15 minutes to go over the multiple choice questions. So if you're quickly scrolling through them, there are a whopping essentially 10. 9 has 2 parts. Essentially 10 multiple choice questions. I want you guys to take your time to sort of go through each of these, select the right answer that you think is correct, and then in about maybe 15 minutes from now, to give you guys enough time to make sure that you read the questions and give it proper thought. I'll come back in about 15 minutes, and then we'll go over each of these individually, talk about them a little in depth, and hit on some of the key stuff that may have been brought up earlier that will relate to each of these questions and why the answers are the way that they are. And then from there, we'll go over the formulation and coding examples, where we start from the model that we had before, and then expand on it, make a couple little changes. What if this? What if that? Things of that nature. And then we'll go over those examples. So for that time, once we get back to this, we'll sort of talk about an intro here a little bit when we come back from the first break. And then maybe give everyone about another 15 to 20 minutes to do the formulation coding part. And then after that, we'll come back and go over those final questions. And that would be it for the exercise part. So feel free to ask questions about the questions in the chat, and about anything else, using the Q&A part of this feature, and then also adding them into Whova is fine as well. So I'm essentially going to turn the camera off for a little bit, and I'll be back in about 10 or 15. Let's say I'm on the East Coast, so it is 2:06. So we'll say 2:20 Eastern time, so 20 minutes after the hour. We'll come back and start going over the multiple choice questions, and then dive into the others after. That was a good question. I might as well say this to everybody. I'll unmute my mic real fast. There is no real grading. Everyone's going to get a thumbs up at the end. But so this is just more for your own purposes. Don't worry about submitting them or anything like that. Just note your answers, write them down on paper, or copy paste, or do whatever however you want to highlight your answers, and then we'll go from there. So no grading here. All right, so I hope that was enough time. Let's share. All right, seems like My screen is back to being shared and everything looks good. Again, we're just going to go over the multiple choice questions. Hopefully, like I said, hopefully there's enough time. And then I'll give you a little bit more time to go over the formulating coding, or do the formulating coding, and then we'll come back to that and wrap up this session. Multiple choice questions. Some of these you might be thinking, they're pretty easy. Maybe not. Depends on how much of the videos you're able to see and your previous, maybe some previous knowledge you have. But if you watched all the videos and everything, and all of this should be, all of this was answered in there. So question 1, which of these are not key components of an optimization model? We were talking about, we listed several key components, one of which was decision variables, parameters, objective function. Hyperparameters is something that we didn't really mention today. So that would be the answer for question 1. Hyperparameters is one of the things that's not there. That doesn't mean that optimization models don't need to be tuned and there are not settings. That is definitely true. These are very complex algorithms that are solving these problems. So there's definitely things that can be changed, settings that need to that can be updated in order to get better performance. So that is something that optimization modeling sort of has in common with machine learning. And that's something that you would set for a machine learning problem. You would set some hyperparameters there about maybe something like a learning rate, or the number of variables that you consider in a decision in a random forest for trees, things like that. But for optimization modeling, for what we've discussed so far, hyperparameters is not part of that set. Question 2. MO, which is mathematical optimization, hopefully you at least caught that part, can be used as a strict replacement for nearly all machine learning problems, meaning any machine learning problem I can do with mathematical optimization. The answer to that is false. That's not what mathematical optimization is built for. We talked about the problems that MO is best suited for. What are the key characteristics that you're looking for? And that's not all machine learning problems. Question 3, machine learning can be used as a strict replacement for nearly all mathematical optimization problems. Again, that is false. That is, we talked about at the beginning, how these two technologies, machine learning and mathematical optimization, how they can complement each other, how one tends to look at predictions and the other looks at prescriptions of prescribing actions and decisions, and how that's a little bit different. How those are very different questions, particularly from a business perspective. But we also went over, notice I mentioned like strict replacement, and it said nearly all and stuff like that. Left myself a little bit of wiggle room, because we did talk about how there are certain like regression problems I specifically mentioned that can be formulated as mathematical optimization problems, because at the root of both, at machine learning, you're trying to minimize an error, or maximize accuracy or things like that. And that's a similar thing to what you're doing with mathematical optimization problems. We were, in our previous example, we were trying to minimize costs. So they have that in common, and there are some formulations of mathematical optimization problems that are machine learning and constrained regression. Lasso regression was the one I specifically mentioned in the video. That's a case where these two things really blend together nicely. And then also, if you do check out our Jupyter Notebook page, we have an example of feature selection using the L0 norm. And I talked about that a little bit during the video as well. So if you're interested in that application, then check out our notebook example on that as well. So that was a little bit of the relationship between optimization and machine learning, and that they are not, one is not a strict replacement of the other, and that you need both, I think. So question 4, which of the following is a type of decision variable in mathematical optimization? right at the top, binary, and that's where and that's one that we talked about as a way to determine alternatives. Am I going to do this? Yes or no. I threw out some other terms that may seem like they could fit in, but yeah, we just talked about continuous, integer, and binary decision variables. So that's question 4. 5, to solve a mixed integer program, a solver may need to solve this many linear programs. This is something that Hassan talked about in his talk, and this is why solving mixed integer programs can be very difficult, is that you can solve possibly exponentially many linear programs to get a solution to a mixed integer program. So and he did a great job of showing that visually and explaining through that why that's the case. And that's why, sometimes MIPS, even with great solvers, sometimes they do take a while to solve, and that's just the nature of the problem type. Question 6, it's required that you or your analytics team develop a deep expertise in predictive analytics before attempting prescriptive. That is false. Again, when linear programming was invented, machine learning wasn't really a thing. So you can get, you don't necessarily need to have a great predictive model before you're saying, okay, what can I do with this? You can use mathematical optimization, again, like I said in the previous video, anywhere along your analytical maturity sort of curve from there. Question 7, the feasible region of a LP will have blank points in it, then its corresponding mixed integer program, assuming that the two models are exactly the same. It's just one has grb equals integer, or grb.integer is your variable type, and the other one has continuous as its variable type. And from what in the video that Hassan had, you sort of shown that the number of integer points in a feasible region is always going to be oops, did I highlight the wrong answer? I think I highlighted the wrong answer. That's this one. That's another mistake on my part. I mixed them up in my head. Sorry about that again. LPs will have more points in its corresponding feasible region than its mixed integer programs. Mixed integer programs, only integer points. LPs have every point. Question 8, unless specified, the default variable type using advars is continuous. That is true. So let's finish up question 9, and then we'll talk about the other sets real fast. So we have a set J, which is a bunch of fruits and berries, and a set T, which is just a set of integers. Adding the decision variable using advars J and advars range 8 will add the same number of decision variables to a model. That is false. If you do J, you'll add 1, 2, 3, 4, 5, 6, 7 variables. Using range 8, you'll add 8. And then lastly, using the sets above, if you advars J and T, and then use advars range 28, you'll add the same number of variables. That is true, because you'll add 7 times 4 is 28, and this is also 28. They won't have the same indexing or anything like that, but you will have the same number. So that's it for the multiple choice questions. Here is the formulation and coding part of it. I dropped in the formulation from before, and then there's a few follow-on questions. So let's see, it is 2:30 now, on a good time. There are, I think, 5 more questions about. So I'll do the same thing. I'm going to cut my video and the mic. And then give you guys a little bit of time to go through those go through those examples, and then I say maybe 15 minutes from now, I will come back on and we can go through those again. Okay, so let's get back to these last couple questions, and then go from there. Let me reshare the old desktop screen. So now we should see the completed exercise set. So I mean, the purpose of this for this bit is, just to get some small incremental steps, apply what we've learned so far, and I understand that a lot of this is maybe pretty new, and it's a little, it's maybe not super easy to pick up, and that's perfectly fine. So but again, this is, small steps, and tomorrow we're gonna sort of do some pick, instead of small steps, you may be taking a little bit larger steps tomorrow. So I hope that we were able to get you off on some solid footing, in order to keep going here. So let's see. Let's tackle these problems. So here is essentially the model. In it looked much longer before, we're scrolling, but this is essentially, this is it, and half of it is reading in data. The actual model itself, is just, these few lines right here. So just sort of shows how a very complex problem, well, I mean, this one isn't very complex, but a somewhat complex problem just boils down to just a few lines of code. So if you run this, you get the same as before. So and again, these questions are meant to be independent of one another, just sort of, if this, what happens? If this, what happens? So the first question is 10A. Whoops, that's 10. 10A is, hey, what's the formulation for this part here? You're told that there's a new policy for transporting widgets from production facilities. It's now required that the minimum number of widgets shipped needs to be at least 20. I don't have the solution from the prior example up, but if you looked at that, there's some instances in which the decision variable is to ship, 3 from one location to another, or 8 or 2, and that may be something that's not practical for your for your business problem. It's something that, like, it may be the lower cost, but you need to think of practicality, and other things that may not be in this model. If you're shipping something, does it require extra trips? Are there people to do it? There's a whole bunch of stuff about this model and this system that we didn't really capture in the LP. So you need to make sure that those things are accounted for as well. So having this new constraint of that we see here, this is essentially saying that every decision variable from P to D must be greater than or equal to 20. So you have to ship at least 20 units, 20 widgets from every location. So for each production facility and for each distribution center. So the code for that is right here. Oops, you're adding a bunch of constraints. XPD must be greater than or equal to 20 for P in production, for D in distribution. You can, there's other ways that you can could have formulated this for part. We had you could come up with other ways of combining these two sets. We had, like, the indices from the cost data frame. We use that for ways of adding variables and things like that. So you may have something that's slightly different here to make sure that you're going through each combination of production facility and distribution location. But as long as that is, as long as individually all of these decision variables are at least 20, then you're getting the job done. Okay. So question 11. The initial widget model M represented a single time period. So it could be a week, a month, a quarter. Suppose we added a time component, which that is something that most of problems like this have. You're not just planning for a single period and like, oh, well, I got the optimal for this. It's going to be the same for everyone. That's not going to be the case. So suppose we added a time component using a time variable or time, set t, and we have periods 0, 1, 2, and 3, representing the quarters of a year. So you have quarter 1, 2, 3, and 4, represented by t is 0, 1, 2, and 3, let's say. Question 11a is use addvar or addvars to create a decision variable in Gurobi Pi that represents the number of widgets shipped from a production to distribution center for a given time period. So essentially what you're doing here is just adding in that last set. It's the same as we had before, but now we're adding in that set t. And so this is how I decided to do it. I just kept the same essentially line of code, and then just added in another set here after the distribution for range 4, where this essentially gives me the 4 time periods that we have in T. There's, again, a bunch of ways you can go about it. You can say T is equal to 0, 1, 2, 2 and 3, like this, and then you can use set T, or you can, it doesn't matter how you decide to do it, as long as you have essentially your production by your distribution by your time. There's different ways to call it, different ways to go about it. So that's how, that gives you an option for defining the set. And then also we talked about a bunch of different ways to write the variables so that they're added. We talked about for loops, so you can actually loop through each of these if we wanted to, something like this. So for P in production, and then this would be for D in distribution, and then for T in range. And then we would have, we always want to put a little, if you're going to do it this way, you got to put like something at the beginning like this. Then you would say X P D T add var, and then name equals prod ship, maybe time, something like that. So this is another way to add all the variables that we'd want. And then we talked about the third way in the beginning of using the index of some data set that you may have. So if we had demand that was different, or costs that were different over each individual period, which is probably the case in real life, then we can use that. So we would have to have a different data set, a different CSV file that has production facilities by distribution centers by time, and what those costs were, and we can use that for example. So there's a bunch of ways to go about it, all coming up the same at the end. Just making sure that that you're using printing out your variables to make sure that they're all there, and then really using that LP file. Really using that LP file in order to make sure that your model is correct. So the last part, question 11b, and this is getting into a little bit of prep for what we have tomorrow. If you want to reference a time period before a certain time, so you have time period T, then you can reference the previous one by using T-1. So using that as a subscript. since t is a set of integers, it's easy to do that, and that's why it's often used. That's why time is often like an integer set, as opposed to saying like a text or a string time period 1, time period 2. So essentially we want to have a new constraint that limits the amount of production a facility can produce to max prod over 2 consecutive periods. So essentially we want to fill in the question marks. So how do we do that? I put most of it here. So essentially what we want to make sure is for two consecutive periods, and then sum up all of that needs to be less than the max production P. So this set of question marks here could be your current time period T, and then you set this to T minus 1. So this is your current period, previous period, and then you're summing that up. That must be less than your production P for all your production sites. But now we also have to say a little bit more about the time, because we can't, we don't have a previous period for time 0. So we need to add in this extra if statement of if T is positive. So T being 1, 2, or 3, because we don't have a time period before that. So needed to, oops, that's over here, this little question mark here. So if for T in range 4, if T is positive. So I think that puts us right at our time period.